Yes, first your questions.
A quadrupole from point charges. How come the odd multiple vanish?
For a quadrupole, let's see. We have plus Q, minus Q, minus Q, right? So let's put the origin here. X and Y. We have the rho, which is, what is the charge density? So saying that charge density is 0 means there is no charges. But I have some charges, right? Well, let's give them some names. This is, let's call this R0, R1. This is minus R1. This is minus R0.
In the special case in the book, they are equal.
Well, those vectors cannot be equal. They point in different directions. But of course, we will be assuming that these distances are the same. They are related. This is the same as this one. This distance is the same as that one.
Is it going to change the result?
Hmm?
Is it going to change the result? If we made the distance?
Well, let's see. Let's see. I mean, let's try to avoid making that assumption in our discussion as long as possible. But let's just assume, for simplicity, that we have these two symmetrical positive charges and these two symmetrical negative charges. So let's see when we will need that assumption. So what are the charges? What is the charge density of this configuration? Hmm?
Minus Q, black delta, R minus R0. Plus Q, black delta, R plus R0. Plus Q, black delta, R minus R1. Minus Q, black delta, R plus R1.
Minus R1.
Plus R1.
Do you all agree that this is our charge density? Do you? Do you agree that this is correct? No? How should I change it?
The last term must be plus.
You mean this one is plus
The other one is minus.
and this one is minus?
No. This is also plus.
Both of them are plus.
Yes. The second term must be minus.
The second term is minus. So what do you think? Hmm?
It's correct.
Now, with this notation, it is correct. Right? Do you insist on your signs or his signs?
No, I'm saying it's correct now.
Now, okay, so this is minus. And these are both pluses. Well, we have a minus Q charges at plus R0 and minus R0, and plus Q charges at R1 and minus R1. So what can you say about rho of minus R? Is it somehow related with rho of r? Or there might be no relation whatsoever? And let's remember one property of the Dirac deltas. A of x is equal to Dirac delta of x divided by the absolute value of a. So what can you say about rho of minus r? Rho of r is equal to rho of r. So the charge density has this property. Now we will be using this property of the charge density to show that some of the multiple moments should be odd. And remember one other property. YLM, let's say we have this whole, the angles corresponding to the vector minus r, is equal to minus 1 to the L YLM, the angles corresponding to the vector r. So YLMs have this property, which for us will be important. Now let's look at QLM. What was the definition? Y conjugate. What else? R to the L maybe?
Yes.
Now let's make a change of variables. This is equal to, let's just, instead of R, substitute minus R. I'm just making a change of variable. So the volume, the integral doesn't change. YLM star, it becomes minus R, rho of minus R, R to the L. Again, I repeat, I just made a change of variables. Nothing else. Well, you see, that is the magnitude of the vector. So if I replace R with minus R, the magnitude doesn't change. Well, the YLM, we already know its property. It becomes minus 1 to the L, YLM star, omega R. Now, rho of minus R, we just said that it, in this particular case, at least, it is rho of R, R to the L. But this is nothing but, so we have, what we had shown is that QLM is equal to minus 1 to the power L. What remains is still QLM. So if L is odd, then QLMs are 0. And remember, the only property that we had used is not that we have a system of 4 charges, 2 plus Q, 2 minus Q. The only 4-point charges, as long as the charge density has this property, over here, we can say that the odd moments are all 0. If all odd moments are 0, then we can also say that the charge density has that property. So that is kind of one of the nice things about studying the multiple moments. If we can study the multiple moments, then we can say something about the charge density if we do not know it.
How can you show the inverse relationship?
Yeah, let's see. Let's try to give a different interpretation of these multiple moments. Rho of R. So it depends on r, theta, and phi. So it's a function of theta and phi. So any function of theta and phi we can expand in terms of spherical harmonics, right? So this is, let me write it in this form, rho L m, which will be a function of only the radial coordinate, times y L m of omega r. Let me use this notation. I don't know, I mean, given the charge distribution, we can determine what this rho L m r will be. Okay, so let's calculate the moments, and let's see if we can relate it to this rho L m r. No, let's calculate this rho L m r, not the moments. Let's calculate directly this rho L m r. How can we calculate this rho L m r? So how do you find the expansion coefficients in a expansion? Well, we have this orthonormal basis, a complete orthonormal basis, the spherical harmonics. They are orthogonal to each other and normalized. So that means that if I take multiply it with YLM star, this rho of R, with YLM star, and integrate over all the solid angles, I obtain rho LM of R. Okay? Now the moments. You see, this almost looks like the definition of the multiple moments. Almost. Not exactly. So to say that it is the multiple to convert it to the multiple moments, QLM, is nothing but we just take rho LM, R, multiply it with R to the L, dl, integrate over R squared dr from 0 to infinity.
If we can we just substitute rho LM of R into this integral, see that it is equivalent to the definition of the multiple.
Let's see. QLM is equal to, from 0 to infinity, rho LM, we said that they are given by integral over the solid angle of YLM star omega, rho of R, R to the L, R squared dr. Integral YLM star omega, rho of R, R to the L, R squared dr d omega. But this is nothing but my volume element. So it is actually there are multiple moments.
Okay, so now we set L rho.
There is one step that I'm kind of missing. You see, what happens is it possible that rho LM of R is non-zero even if QLM is 0? Now, that doesn't, I mean, we are saying that all odd QLMs for odd L are all 0. That is what will be our assumption, and try to prove that rho is symmetric from that assumption. But, I mean, just looking at this definition, I don't think I don't see how. So QLM is 0, rho LM might be 0, might not be 0. Its integral might be 0. So let's look at this one. This was our definition. And remember what we are trying to prove, what he wants. My claim, now I'm not so sure if it is justified, that if QLM is 0 for L odd, this implies that rho of R is equal to rho of minus R. This is what we are trying to see, whether correct or not. Now we said that rho of R, we can always write it in this form. So rho of minus R will be equal to rho Lm of R y Lm of omega minus R. Well, the magnitude doesn't change. This is equal to minus 1 to the L rho Lm of R y Lm of omega minus R, no, plus R. So rho of minus R is equal to rho of R if and only if rho Lm of R is equal to 0 for L odd. If for L odd rho Lm is 0, then only the even L terms survive. For even L's, minus 1 to the L is 1. So rho of minus R becomes rho of R. So this is definitely true. Now, the claim that rho Lm of R is equal to 0 if QLM is equal to 0, I don't think we have a proof for that. So if you have some charge configuration for which QLM is non-zero, but rho Lm is 0, it might be even for a single value U of L, then it won't be odd. But nevertheless, I mean, you see, the multiple moments, they are mainly related with how the charge is distributed. So maybe there is no strict one-to-one relationship, or maybe there is, but we cannot see it at the moment. But if you can somehow determine the multiple moments, you know what the charge distribution is. You can determine what the charge distribution is.
How many multiple moments do we have to determine?
All of them.
They are infinite.
Are there infinitely many? So that's another question. So what is the charge distribution that you would like to determine? You would like to know the charge distribution of what? You're not curious about the charge distribution of anything?
Atoms.
Atoms. Well, atoms are quite, as far as we know, they are quite symmetrical. So we don't expect them to have many multiple moments. They would have a few, And if we can show that actually we have a large, the monopole moment for neutral atoms will be 0. If they have higher multiples, you will get 1 or 2 of them that are large, the other ones will be very small. So since they are very small, they will just bring small corrections to our understanding. So the first 2 would be enough for us. What else? Hmm? Yeah, they are atoms.
Let's say a charged cube.
A charged cube, where do you see that?
Imagine.
In real, I mean, for example, you would like, I mean, a charged cube, you would better probably take some device that measures the local electric field and bring that to the cube. And you can make, I mean, for macroscopic objects, you can just go there and measure it by measuring the electric field. But for example, the molecules, you cannot just go to a molecule and make measurements on the atom or the molecule or the nuclei. You cannot just go there and make bring your device close to the nuclei and make measurements. So how do you measure the atom or the nuclei? If we can measure it somehow, then we know something about the charge distribution, but then the question is, how do we measure it?
Rather than measure our effects, we try to affect the atoms.
How?
Applying external electric field or something else.
Okay.
Then we measure the change of it. So we might have some idea about what the charge distribution is.
So that brings us to the question of how do the charge distribution is influenced by external effects, an external electric field. How does it interact with an external electric field? You have a charge density. You apply an external, let's say, potential. This is basically the energy of the system in the external field. You can basically do the same thing. Rho of R will be, let's say, rho of R0 plus the delta. What is R0? Well, you can choose it to be arbitrary, but what we want to do is expand in delta. But if you want to expand in delta, you should better make sure that delta is small. So rho R0 is kind of arbitrary. Somebody was asking on Wednesday, where is this dipole? It is in R0. So it is kind of arbitrary. But nevertheless, you should choose in a way that delta is small. So it should be somewhere inside your charge distribution, if you have some localized charge distribution. Well, then you can make this expansion. And you will see that the energy of your system is actually kind of a multiple expansion. Or let's say not rho, but V. You expand the V. Because V of R0, or the derivatives of V at the point R0, you already know. It's what you apply. And furthermore, they are constants. You can just take it out of those integrals. And by just some rearrangement, you will see that E is nothing but V of R0 times Q plus E dot P, E at the point R0, that the dipole moment plus other terms.
I think we assume the third term is zero.
Hmm?
I think we consider the third term is zero because we don't have any charge that is generating the electric field at R0.
Not really. You see, we are not taking the Laplacian of V. That's not the Laplacian of V. But we do, you're right, there is a term that we ignore. We set to 0. Let's look at that term. We have the d cubed r, d cubed delta. I just made a change of variable from r to delta. Delta I, delta j, rho of r, del I, del j, acting on VR0 divided by 2 factorial. That is the last term.
We say that electric field is equal to this, but its unit is...
Not the electric field, this is the energy.
Oh, okay.
This is the energy.
What is delta I, delta j? What does it mean?
Let me use a different symbol. We-
Okay.
I made this change of variable, R0 plus
The component.
eta. It's the component. Now what I will do is this is equal to d cubed eta, eta I, eta j minus Kronecker delta I j over 3, eta squared, rho of r, rho of delta, eta, multiplied with del I, del j, v of r0 divided by 2 factorial. Well, I could do that because Kronecker delta ij, del I, del j acting on v. This is nothing but the Laplacian acting on v, which is supposed to be minus 4 pi rho prime at r, rho prime being the charge distribution creating the external potential. There are no charges. The charge distribution that's creating the potential is out of the system, not at the position of the system, so this is equal to 0 at R0. This is the term that is 0. Now, furthermore, I can do one more step. And I can write this term as 1 over 2 factorial del I, del j minus Kronecker delta ij over 3 that term is 0. Anyway, it just looks more symmetrical. That's why sometimes we add it. That's the Laplacian of v, that is 0. So this is nothing but the quadrupole moment. So basically the energy depends on the, let me add, here we have the Qij, let me write it Vij, etc. So this is the energy of the system. Well, the total charge of the system is most of the time the easiest to measure. You just let it move in a magnetic field, let's say, and see if it bends. If it bends in a magnetic field, then you know that it has a total charge, Q. So Q is kind of trivial to measure. Now comes the second term. Especially if you are interested in the subatomic particles or molecules or nuclei. What you do over there is you apply an external electric field. Then, if you know the spin, not even the spin, you apply an external electric field E of R0. So depending on the orientation of P, the system will have different energies. If you add the quantum mechanical influences, it means it will have different energy levels rather than continuous energy distribution. And since we are talking about charges, charges always emit photons, light. So it will start making transitions between these energy levels by emitting light. And you can measure light. So by measuring light that is emitted, you can determine what is P, what is the dipole moment of the system. Of course, we will also see that the dipole moment will be created by the external electric field, though. So that is kind of, let's say, a bit problematic. So you can measure a dipole moment that doesn't exist before. But at least you will be able to measure what is the dipole moment that the system acquires if you put it in an external electric field. And by changing the electric field, measuring the dipole moment in each electric field, you will see how the dipole moment is related to the external electric field. Well, if you are interested in the quadrupole moment, you put it in a non-uniform electric field because the dipole moment is, the easiest way to measure the dipole moment is put it in a uniform electric field, so the other terms are all zero. There's no interaction with the quadrupole moment. Well, you put it in a non-uniform electric field, and you can also arrange your electric field such that it is zero at the position of your charge distribution. So there is no contribution from the dipole moment, but there will be contribution from the non-uniformity of the electric field. And again, you just measure the energy levels, and from that energy levels, you can determine the quadrupole moment. Well, this kind of works for, let's say, atoms, relatively large objects. Now, if you go to nuclei, also because you can hold atoms in place so that you can prevent them from motion. But if you want to measure, let's say, nuclei, it's not so easy to keep hold of the nuclei. They will be moving. And to create them, most of them at least, you will need accelerators which create nuclei or subatomic particles at very small distances that move quite fast. So there is no chance of, okay, let me apply an electric field, a constant one, and see what happens. You don't really get that chance. But what you do is you just let them interact with light. You shine some laser light, or you just scatter some electrons off them, because the electrons basically interact with light. And then you basically do the same thing. You just look at how they interact, and from this information you try to extract whether the system has a dipole moment, quadrupole moment, etc. But especially for subatomic particles, things is kind of easy because you don't have infinitely many multiples. You have at most just a couple of them.
Because the rest are negligible.
Not negligible, zero. Especially for fundamental particles, point particles. You cannot even have a dipole. You will see, we can have magnetic dipole, but not electric dipole. Well, you cannot have, but they are negligible, let's say. It's like 4 or 5 orders of magnitude smaller than what we can experimentally measure, if the standard model is correct. So basically, if we can measure the electric dipole moment of, let's say, the neutron even, if we can measure it, and we are trying to measure it, that will tell us that our theories are wrong. Because our theory predicts that we shouldn't be able to measure it with the current precision. If we can measure it, that means the prediction of the theory is wrong. So we need some new theories.
Is it possible to create dipole moment electron charge by using electric field?
Well, the problem is the dipole is basically a displaced charge distribution. A point charge doesn't really have this charge distribution.
If we apply,
Hmm?
but if the electric field is enough,
Hmm?
if the electric field enough to
If you have a very, very strong electric field, so strong that you can create, let's say, particle-antiparticle pairs from the vacuum, yes.
If we do that, if we manage to do that, is it going to decrease the intensity of our electric field? If we manage to do that, is it going to decrease the intensity of our electric field?
Well, if we manage to do that, we will have other concerns. But yes. For example, you can induce a dipole moment of the neutron. Well, it's not a point particle, but that you can do it because the neutron, as far as we know, is a bound object of many quarks and quarks, which can have positive and negative charges. So you can basically pull the positive by applying an external electric field. You can pull them in different directions, creating a dipole. When you have this quantum mechanical picture, things get a bit more complicated because even at what you call a single point particle isn't really always a point particle.
in the first example, can you show it? If we remove minus Q charge and set the origin here,
Mhm. So we remove one of the minus Q charges, set the origin at the position of the minus Q charge, okay?
And can we say that the total dipole moment is the superposition of these two dipoles?
Not the two. Yeah. Okay, so let's do it like this. We know that rho is equal to, suppose you separate your charge distribution. Rho 1 plus rho 2 plus rho 3. You just separate them by whatever convention you want. Then the multiple moments, they were defined in this form. Well, they are also, they split. So if you just break your charge distribution, calculate the multiple moment for each one of them using the same center, that will be crucial. Then the total multiple moment will be just the sum. For example, in this configuration, what is the dipole moment? If you want to calculate the dipole moment by breaking it up, you can just take it. Group them like this. Calculate the dipole moment of each one, sum them up. So you see that each one has the same dipole moment, but they are pointing in opposite directions, so the sum is 0. So that's why we can straight away say that the dipole moment is 0. Or you can take the same object, group it in this form, add the dipole moments. Or this was our object. Divide your charge distribution into 4. Calculate the dipole moment of each one and add them up. A point charge, if it is not at the origin, does have a dipole moment. All of them are the same. So your answer to your question, yes, you can just divide your system into parts and add the dipole moments. But you see, if you have plus q, minus q, plus q, you said that let's remove one of them. The dipole moment of this system is not equal to the dipole moments of, no, this is minus q, this system plus this one.
Instead of minus q, if we have minus 2q, so the result.
I mean, it doesn't matter. You say if you have, let's say, plus q, minus q, plus q, plus 2q,
there's no plus 2q. Instead of minus q, we have minus 2q.
minus 2q, okay.
Remove, yes.
Okay. Then this system, I can of course separate it as I have minus q, another minus q, they are at the same point, so I have a minus 2q charge. So this system is this one plus this one. This we can do. So the basic idea is that whatever separation you have of your charge density, then the multiple moments would be just calculate the multiple moment of each one and sum them up. And again, I repeat, they should be at the same origin. They should be calculated with respect to the same origin. Now, in these cases, the choice of origin doesn't really matter about when you are calculating the dipole moment, because we had seen that the dipole moment is independent of the origin if the system is neutral. But if the system is not neutral, like a point charge, then the dipole moment changes if you change your origin. So this system is neutral, and each part of our system is neutral. So wherever you choose your origin, you will get the same result. But if the parts were not neutral, then you have to stick with the same origin for your coordinate axis to calculate the moments.
That is just for the
Any moment.
the freedom of choice of the origin is only for the dipole.
You don't have, I mean, you are free to choose your origin. You always have that freedom. The question is, are the multiple moments, do the multiple moments depend on your choice of the origin? And it turns out that the Elf moment depends on the origin if the moments of lower L is non-zero. So QLM depends on the choice of the origin if QLM, QL prime M prime is non-zero for some L prime less than L. For the dipole, the lower moment is the monopole, which is the total charge. So if total charge is zero, then the dipole is independent of the choice of the origin.
Is converting our results calculated with respect to one origin to another is easy or?
Let's try. Let's see. So we have this charge distribution, whatever it is. Then we have one coordinate system and another coordinate system with a different origin. So of course the functional form of the charge density will be slightly different. Let's say this is the coordinate O, coordinate axis O. This is the other one is O prime. This is the, let's say, the vector R. So R prime is the position vector relative to O prime, and R is the position vector relative to O. So R is actually R prime plus R, and rho of R is equal to rho prime of R prime, which is rho prime of R plus capital R. Yes, there is a sign change. R prime is R minus capital R. And let's say QLM is equal to rho of R YLM and QL prime M prime rho of R prime, rho prime R prime YLM of omega prime d cubed R prime. So let's make a change of variable. Instead of R prime, let me write R minus small r. So QL prime M prime will be equal to rho prime of R minus R, YLM of omega of R prime minus R, d cubed R, d cubed R. Right? So Q, no, these are L M prime is equal to rho of R. Now there is also the R to the L. YLM omega R prime minus R. Well, here we had the R prime to the L, which is now R minus R magnitude square to the power L. D cubed R. Oops. So it's not always trivial. For L is equal to, let's say, 1, we know what YLM is more or less, so we can proceed a bit further. Well, for each L, you should actually just do it. Now, the simplification for L is equal to 1 is that R times YLM. These are basically components of L is equal to 1, Ri. Various components. So we know how they transform, so that makes it easy. Now for the other ones, we can still proceed. We know the addition theorem for spherical harmonics, so that will allow me to write this YLM R minus R in terms of YLM of R. And this absolute value to the power L, well, we have to do it case by case.
So the addition theorem had to do with YLM R minus.
What was the addition theorem?
Remember it had to do with the addition that permanent.
Well, gamma is basically the angle between, this cosine gamma will be somehow related to this one. I mean, it's not straightforward, but there should be some relation. You see, what is omega R minus R?
So gamma is the angle between the vector pointing in omega and the vector pointing in omega prime.
Let me see. This is our vector R prime, right? This is the vector R. No, it was the other way around. Small r minus capital R is this vector over here. Now, omega R minus R, we should somehow relate this angle over here. This is nothing but omega R minus R to this angle over here. The solid angle in one reference frame to the solid angle on the other reference frame. That is what we should somehow do. But even if it is not this one, you see, this is the angle of the point in the other reference frame, which depends on the angles on this reference frame. So I should be able to write that angle, those solid angles. You see, I should be able to write YLM omega R minus R in terms of YLM omega R. Let's say M prime with some coefficients that depends on, let's say, the angles of the vector R. This should be possible because YLMs are complete. Now, if we do this, if we write it in this form, QLM prime will be equal to rho of R sum over L prime M prime, this phi L prime M prime, which I have no idea what they are, y L prime M prime omega R times, well, let's see, this R minus R to the L, I can write it as a Taylor expansion in terms of R to the L with functions that will depend on the large R and gamma, the angle between small r and capital R. Well, things start to get more and more complicated, but I mean, case by case, you should express one in terms of the other ones. The simplest is the dipole. Now, before I forget, for next week, we are skipping chapter 4. I mean, the chapter 4, if you are interested in complex analysis, I do advise you to study it. The basic idea of chapter 4 is that if you have analytic functions of complex variables, they are solutions of the Laplace equation in 2 dimensions. So I just find some analytic function, so you have a solution of the Laplace equation. So that's kind of nice. Another thing about the complex analysis is, well, 2-dimensional problems, basically, they have this translational symmetry in one direction. Like you have infinite planes, infinite at this one axis. So everything looks the same along that axis. So those systems are basically 2-dimensional systems. There's nothing depends on that dimension, nothing in the potential. And another nice thing is that, for example, you can change you can just change coordinates. Instead of one complex variable, x plus iy is your complex number. So the 2-dimensional problem is now a problem of a complex variable. Any analytic function of z is a solution of both the real and imaginary parts in terms of x and y. Because in these coordinates, Laplacian is actually derivative with respect to z and derivative with respect to z bar, the conjugates of z. So if you have a function of z only, you automatically have a solution. Now, furthermore, you can just transform z to another variable, omega of z, change of variables. And you take this function, define f of omega, or let me put it in this way. Laplacian with respect to z is proportional to the Laplacian with respect to omega, if omega is, this transformation is analytic. So this is nice because there are already functions that would transform, let's say, such regions, an arbitrary shape, arbitrary polygon. This is z in the z plane. In the omega plane, they are this one. We already know the solution in the omega plane, but they will also be a solution in the z plane once you substitute omega of z there. So we can solve such arbitrary polygon shapes, polygon tubes. So this is kind of fun, I would say, in complex analysis. So if you are interested, have a look. The next chapter is, chapter 5 is what we will start next week. That is the electrostatics in matter. Now, what we will be doing in electrostatics in matter, basically 2 things. First of all, we are not really interested in the electric field everywhere. Because, I mean, classically speaking, at least, every matter is made up of point charges. And at the position of the point charges, the electric field is infinite. Well, quantum mechanical effects kind of average them out. And even practically, we can only measure the average values over a region. So we will be talking about the averages of electric field in a given region, in a given volume. And if you have this material, let's see, the electric field at this point, when we talk about the electric field at that point, we will consider the average over, let's say, a sphere. But that point, the electric field, the average of the electric field in that sphere will receive two contributions from the atoms outside. Well, if there's an electric field, the atoms outside will be polarized, which means if there's an electric field, the negative and positive charges will move in different directions, creating a dipole. They are very small. They are very far away from the point that I am studying. So I can use the dipole approximation. So we have this dipole, the potential or the electric field created by a dipole. But the potential created by a dipole, we know how to take its average. We had already studied it. There are also the dipoles created in our sphere, but we also know how to calculate the average of that one. So those will be the two averages which we had already studied as examples. So we will just sum them up. Now, another interesting thing that we will be using is, none of you asked, okay, we have these dipoles. We had calculated these multiples, so we know what kind of an electric field a given charge distribution creates in terms of the multiples. But we also know how the given charge distribution is influenced with an external electric field in terms of the multiples. So we know, for example, that a dipole will interact with an external potential through this term. This will be the interaction of a dipole with an external this will be the potential created of a dipole. And if we put another dipole in this, there will be an electric field, corresponding electric field, which should be 3p dot r hat minus p or r cubed. So we have this dipole over here. Let me call it P1. And let's imagine we have some other dipole somewhere else, P2. Well, we know the electric field that P1 creates at the position of P2. And we can write the potential energy of the system, which is nothing but minus E at the position of P2, scalar product with P2. This will be the potential energy. And this will be equal to minus 3 P1 dot r hat P2 dot r hat minus P1 dot P2 divided by r cubed. So this is the potential energy of my system. Now my system will try to minimize this potential energy. Now the question is, which configuration minimizes potential energy? Which orientation of the dipoles? For example, I have one dipole over here, the other dipole over here. This configuration, they are aligned. Right?
The same line. The two vectors must lie in the same line.
Well, they are lying in the same direction. Two vectors are in the same direction. Not the three vectors, if that's what you are talking about. Now let's see. This is one orientation. This is the other possibility, let's say. This is the third case. I'm assuming that their separation is the same. And this is the fourth case. So we have kind of interesting four cases. Which one has the minimum potential? First and the fourth. Okay, let's see who have read the chapters. Yes, which one has the lowest potential? Second and third, okay. First and fourth is second and third. Last one. First and the last one. No idea. Well, okay, let's see. 1/3 has read the chapter. This is an example in the book. Let's see. This is my R hat. What is P1 dot R hat? In this configuration? Hmm?
The first configuration,
We will be studying the energy of each one of these configurations, one by one. Here I have the expression of the energy, so I know which terms I should calculate. Now for this configuration, what is P1 dot R hat? 0, they are orthogonal. And so I only receive a contribution from this minus E is outside. So the only contribution I get is from the last term, what is P1 dot P2? Yeah, it's just the product of the magnitudes, they are pointing in the same direction. So U is equal to, in this case, U is equal to P1 times P2 in product of the magnitudes divided by R cubed. Let's just call it omega 0. Just a name. Let's look at the second configuration. What is P1 dot R hat? P2 dot, the first term is again 0. What is P1 dot P2? It's minus the product of the magnitude. So the energy here is minus U0, minus omega 0. Let's look at this one. Again, this is R hat. What is P1 dot R hat? Minus P1. P2 dot R hat? Plus P2. So U is equal to minus 3 minus P1 P2. What is P1 dot P2? They are pointing in opposite direction, so it's minus the product of the magnitudes divided by R cubed. So this is minus 3 plus 1, that is minus 2. U is equal to 2 omega 0. Now here comes the last one. Again, this is R hat. What is P1 dot R hat? P2 dot R hat. So U is equal to minus 3 P1 P2. What is P1 dot P2? P1 P2 times 1 over R cubed. So this is minus 2 omega 0. So this is the configuration that has the lowest energy, not the other ones.
I asked before about the position of the dipole. I meant the R cube. Can I draw the book? If we have, let's say, some charge distribution, some dipole moment, and on the inside, the origin, we have another charge distribution with some other dipole moment. What R cube?
Well, you see, when you are defining or measuring the dipole moment, calculating the dipole moment, you are already choosing an origin. That is where your dipole is.
But here, they seem to be at the same origin. R seems to be 0.
Okay. But you see, then the problem is when we are using these expressions over here, you see these expressions, the potential created by the dipole and the electric field created by the dipole, they are valid if you are far away from the dipole. So basically, if you choose the origin of both dipoles to be the same, you cannot use these. They should be separate. Well, this is the minimum energy configuration. Well, the dipoles tend to, if you just have two of them, they tend to align in the direction connecting them. But what we will be basically assuming, I mean, you see this configuration. No, okay. This configuration kind of has a large end. Anyway, so the idea is they will be aligned. Of course, in a given system, you will not have just two dipoles. You will have many dipoles. But nevertheless, they will tend to align. So that will be one of the important things in the next chapter. Especially if you furthermore, if you put an external field, they will also align the dipoles. Now, can you tell me a reason why, for example, this configuration is more favored than this one, if we just compare the two? You see, this is the most favored one. This is the least favored one. If we have this simple dipole picture, would you expect this result from the simple dipole picture? Okay, this just gave us, we explicitly evaluated, etc. We obtained this result, fine, but can you actually justify it by a simple dipole picture?
Yes, because the positive charge is close to the negative charge.
So that's basically the idea. So you see, although we are showing the dipoles as just point charges, a dipole is basically a separated positive and negative charges. So a dipole in this direction means I have positive charges here, negative charges over here. And the dipole in this direction here means positive and negative over here. So basically negative charges attract. In this case, we have the negative charges looking at each other. So they wouldn't like to be close. Now if you look at the other cases, for example, in this first case, we have the positive charges are above, negative charges are below. So if you look at the electric field created by this charge, by this dipole, the electric field will have this form. This is the electric field line created by the first dipole. Now the electric field starts from the positive charge, goes to the negative charge. This is the electric field created by the first dipole only. First dipole. So this electric field will push the positive charge of the second dipole downwards, not upwards. So that is why the second distribution is more stable than the first one. So here the electric field will have this shape. So the second dipole is aligned in the direction of the electric field. Now, without doing an actual calculation, I wouldn't have a simple explanation without using any computation why this one is more favored than the other one. I can probably say that the first and the second one, sorry, the second one. I cannot compare this one, the second one and the most stable one, but at least the last two and the first two we can get a simple understanding. So let me ask you a question about our previous topics, not this week's.
Is D large?
Hmm?
Is D is large?
No, they're not point objects.
Are these spheres uniformly charged? Or does it-
Well, they are conducting. Will they be uniformly charged?
Only the middle.
Hmm?
Only the outer surface.
Okay, will they be uniformly charged on the surface? Uniformly distributed on the surface?
Not necessarily, but we can assume.
Hmm?
Can be assumed.
Is it justified? You can of course assume it, but is it justified? Now, if one of the spheres were absent, then you can of course assume that it is uniformly charged.
Is iterative approach acceptable?
Hmm?
Iterative approach.
Okay. Tell me. Everything is justified.
Assume one of them is a point charge at the origin, at the center,
Okay.
and solve for the other one.
Solve for the other one. Solve for what for the other one?
For the charge distribution of the other one.
Okay, so if we assume, let's start. You are saying that this is a point charge over here. All right. Then we already know the method of images. We don't need to find all the surface charge. We know that if we have a conducting sphere, and if there is an external point charge, the surface charge of the conducting sphere acts like a point charge over here, and another charge on the center, so that the whole thing has the total charge minus q. So that we already know, right?
Then
Do you agree? Do you remember? So let us solve that problem first. We have a solid sphere that contains a charge, total charge minus q, and we put some plus q over here. So how do we solve this problem? So the distance is d, the radius is r.
first we assume that it's grounded, find the function for the first charge, for the image charge.
So you are saying here we have minus q times r over d, and this distance is r squared over d. Hmm? And then we have the total charge is not minus q r over d, the total charge is minus q, so we have to put at the center another charge minus q times 1 minus r over d.
And then we check if it satisfies our equation or
Well, this plus q charge and minus q r over d makes the make the surface of the metal zero potential. Now, this central charge over here, since it's at the center, it increases the potential at the surface of the sphere to some constant value. So, with this configuration, the surface of the sphere is an equipotential surface. And the solution of the potential with these charges, all these three charges, satisfies the Poisson equation outside my sphere. It is perpendicular to the surface of the sphere is an equipotential surface and gives me the total charge inside the sphere as minus q. And those conditions uniquely determine the solution. So the solution is unique.
Can you repeat the one about the potential?
Well, you see, the uniqueness theorem, we had, did we discuss the uniqueness theorem? Yeah.
Let's consider about the potential at the boundary.
At the boundary is constant, plus the charge on the inside that sphere is minus q. So those conditions, as long there is a single function that satisfies all those conditions, and our function does satisfy all those conditions, and hence that is the only solution that satisfies all those conditions. So you were proposing that let's replace okay, so at least for this problem we are kind of done, right?
And so now we retain that we unsolvable 2-point charges.
Well, let's see. We will have how many? We have two images. Each image will have two images on the other side. And so
And we continue to increase.
mhm.
It will continue to increase, I guess.
Yeah, we will have infinitely many images. Let's go for a simpler solution, simpler problem. What are the equipotential surfaces? Let me ask this question first. Let's see, at the point R, which let's say this is the x, y, z. This is, let's say, it's at the origin. This is, let's say, it's at the point D, 0, 0, just for simplicity. I mean, I can choose the x-axis to be connecting these two point charges. Now, the potential at the point R, or x, y, z, this is equal to q over x squared plus y squared plus z squared, square root, minus q over x minus d squared plus y squared plus z squared under the square root. Well, I don't need to worry about the y squared plus y and z separately because it only depends on y squared and z squared. So the potential at the point x rho is q over x squared plus rho squared, square root, minus q over x minus d squared plus rho squared, square root. Now let us find the equipotential surfaces. This should be equal to, let's say, q times some constant. That constant will tell me what is the potential of my equipotential surfaces. I don't want to write these q's all around, so that's why I define that constant as q times c. So 1 over x squared plus rho squared to the 1/2 should be equal to c plus q over x minus d squared plus rho squared to the power 1/2.
Not Q, one.
No, 1 over. Or 1 over x squared plus rho squared should be equal to c squared plus twice c over x minus d squared plus rho squared to the power 1/2 plus 1 over x minus d squared plus rho squared. I just want to find the relation between x and rho. I want to get rid of these. Well, I have this relation already over here, but I'm just trying to convert it to a form that is simpler to interpret. So I just want to get rid of those square roots and see what I have. So 1 over x squared plus rho squared minus 1 over x minus d squared plus rho squared minus c squared. This is equal to 2c over x minus d squared plus rho squared to the power 1/2. Let's take it square once more. This thing squared will be equal to 2c 4c squared divided by x minus d squared plus rho squared. Well, let me just combine these factors for the time being. I would get x minus d squared minus x squared divided by x minus d squared plus rho squared, x squared plus rho squared minus c squared. All of this thing squared should be equal to that one. Well, if I'm not wrong, this should be a sphere. Well, the center will also depend on C. So the center will change. Let's see, do we have time? Yes, we have some time to simplify it. Now, if this is a sphere, now we have to, of course, still identify where this shape is. If this is a sphere, it just tells me that instead of each one of those spheres, I can just replace a conductor. And nothing will change, because basically that is what the method of images is about. In the method of images, we are replacing conductors by point charges, such that that conductor will be an equipotential surface. But that is based on the fact that if you can replace, in fact, any equipotential surface by a conductor and just ignore the charges inside that conductor. And nothing will change out of the conductor. Of course, you just have to make sure that your conductor is at the potential of the equipotential surface. That's the only thing you have to pay attention to. If that is satisfied, then you are done. Nothing will change. So if the solution of this are spheres, as I claim, we have to check. If they are spheres, then I can just replace those spheres by conductors, and we are back to the solution of this problem over here. It will be just, where should I put the image charge? Well, if my claim is correct, then in the iteration method, we had to have infinitely many images. At each iteration, we have to find an image charge. If my claim is correct, it should be enough to have only 2 charges inside the conductors. Then, of course, we have to determine their position with the requirement that those surfaces should be equipotential surfaces. And then we are done. Once we identify those 2 points, we are done. Of course, there's still my claim that this determines a sphere. Let's try to simplify it a bit. maybe not to the end. So we have 4c squared divided by x minus d squared plus rho squared. This should be equal to, I can open up that parenthesis over there, and I will get d squared minus twice xd divided by, let me call this delta 1, this one delta 2, delta 1 times delta 2 minus c squared squared, 4c squared divided by delta 1. This should be equal to c to the 4 minus twice c squared d squared minus 2xd divided by delta 1 delta 2 plus d squared minus 2xd divided by delta 1 squared delta 2 squared. Well, this still doesn't look like a sphere. It will be, I mean, when I equate the parentheses, etc. Let's see. Let me multiply this one by delta 1 delta 2 squared, this one delta 1 squared delta 2 squared, this one delta 1 delta 2. 4c squared delta 1 delta 2 squared should be equal to c to the 4 delta 1 squared delta 2 squared minus 2c squared. Well, this is in fact delta 2 minus delta 1. And this one is, here I have this square of this 1 plus delta 2 minus delta 1 squared. Which one?
Minus 2c squared.
No, delta 1 times delta 2. And what else did I miss? Now we need to solve this one, or simplify it. So let's see. Delta 1 squared. Here we have c to the 4 delta 2 squared. And where else I have delta 1 squared? Here I have a delta 1 squared, and that is plus 2c squared delta 2. This term, I wrote this term, and then I have this term over here, which is plus 1. This is the coefficient of delta 1 squared. Plus in delta 1, I have a delta 1 over here, the coefficient minus 2c squared delta 2 squared, and 1 delta 1 over here, minus 2 delta 2, and 1 delta 1 over here, minus 4c squared delta 2 squared. And a term that doesn't contain any delta 1 and delta 2, any delta 1, is over here plus delta 2 squared. This should be equal to 0. And I don't see any simplification. Let's ask some computer to do it for us. But if I'm not wrong, the equipotential surfaces, well, you see very close to the minus q charge, plus q charge, very close to the minus q charge. Well, the plus q charge will not have any influence. I mean, we would expect them to be almost spheres, at least, if not exactly. So they will be almost spheres. Now what happens is as you increase the potential, they should keep on being spheres, but the center should be shifting. And the potential is increasing now. Eventually, when you reach the zero potential, the center of those spheres will go to infinity, and they will have infinite radius, but here they will be just planes. If you keep increasing further beyond zero, the potential, equipotential surfaces, now the center goes to the infinity at the other side and starts approaching. You get such equipotential surfaces. So just pick any two of those equipotential surfaces, replace them by a conductor, and you are done. Of course, there is still the problem of proving that they are spheres. I might be wrong. I was sure before trying to solve this, I'm not so sure. But they should be spheres. Anyway, last questions for today. So see you on Monday. Your new prayer report is already on Not to Class. Yes.